Session 51, a fundamental property of exponents. We're going to continue on here with our exponents. In the previous session, we addressed exponents in the power of 10, and in particular, how that creates or helps to create the scientific notation system. And here we'd like to take it a little bit further. On this screen here, I'd like to see if you can detect a pattern. Here's the question: 10 times 1,000. What's that equal? Well, it equals 10,000. But let's rewrite this with using our exponents, base 10. How would we rewrite 10 using an exponent in a base of 10? Well, 10 is the same thing as 10 to the first. And we're going to take that and multiply it by 1,000. Well, how would we rewrite 1,000 using 10 with exponents? Well, 1,000 would be 10 to the third. 10 times 10 times 10 is 1,000. How would we do that with 10,000? Well, 10,000 is 10 to the fourth. 10 times 10 is 100, times 10 is 1,000, times 10 a fourth time is 10,000. So 10 to the first times 10 to the third equals 10 to the fourth. Let's take a look at our second problem here. 100 times 10,000 equals 1,000,000. How would we rewrite 100 using 10 and exponents? It would be 10 to the second, 10 squared. What about our 10,000? Well, 10,000 is the same thing as 10 to the fourth. And lastly, 1,000,000 is 10 to the sixth. So in our second problem here, 10 to the second times 10 to the fourth equals 10 to the sixth. Lastly, how would we rewrite this third problem? 10 times 10 equals 100, using just 10 with exponents. Well, 10 is the same thing as 10 to the first. We're going to multiply it here by 10 to the first. And that's going to equal 100. Well, 100 is the same thing as 10 to the second. So for our last equation, our last problem, 10 to the first times 10 to the first equals 10 to the second. Do you notice any pattern about the relationship between the exponent over here and our answer compared against the exponents that are over on the other side of the equation? Well, the exponent that you end up with is actually the other two exponents added together. Here we have a problem. 10 to the first times 10 to the third. We have the same base in both problems. The base is 10. The same base is being raised to an exponent of 1 here and to an exponent of 3 here, and the resulting answer gives us 10 raised to the fourth power. Down here, 10 raised to the second times 10 raised to the fourth gives us 10 to the sixth. And in the last one, 10 to the first times 10 to the first equals 10 to the second. The pattern is when you're multiplying numbers together that are the same base, you simply add their exponents together to give you the answer. So what is 10 to the first times 10 to the third? Well, since we have the same base, our answer is going to be 10 to the 1 plus 3. 1 is our first exponent, 3 is our second exponent, 1 plus 3 is 4. So 10 to the first times 10 to the third equals 10 to the fourth. Over here in our second example, same base, 10 to the second, 10 to the fourth, so our answer is also going to be in a base of 10, and we take our exponents and add them. 2 plus 4 is 6. So 10 to the second times 10 to the fourth is equal to 10 to the sixth. And lastly, 10 to the first times 10 to the first is going to equal 10 to which power? 1 plus 1 is 2. 10 to the first times 10 to the first is going to equal that 1 plus 1, which gives us 10 squared, or 10 to the second. That then leads us to the statement of our first law of exponents, and that is any number x raised to the a power multiplied by that same number x raised to the b power can be determined by just leaving your same base x as it is and then taking the exponents for x and adding them together, a plus b. And then the stipulation or requirement here is that a and b are both positive integers. So that's our first law of exponents. Well, let's come down here and take a look at a couple examples. Here we have 4 to the third times 4 to the 11th. The question, first of all, is do we have the same base in both of these? Yes, the base is the number that's being raised to the exponent. Our base here is 4, and our base here is 4. So that corresponds to our first law of exponents. We have the same base in both of these numbers here that are being multiplied together. With that being the case, we keep the same base for our answer. So the question is then 4 to the third times 4 to the 11th equals 4 to what power? Well, since we have the same base, we add our exponents together. 3 plus 11 is 14. So 4 to the third times 4 to the 11th equals 4 to the 14th. Let's come down here and take a look at our number 17. We have a separate problem here. 17 to the second times 17 to the third. Do we have the same base? Yes, we do. 17 is our base here, and 17 is our base here. Using our first law of exponents then, our answer is also going to have a base of 17, but the exponent answer is going to be the exponent that are used over here added together. 2 plus 3 is going to be 5. So 17 to the second times 17 to the third is going to be 17 to the 2 plus 3, which is the same thing as 5. Let's take a look at one final question here, which is a combination not only of a number with exponents, but other constants being multiplied together as well. Here's your problem. 5 times 10 squared times 4 times 10 to the third. What does that equal? Well, first of all, we can see that everything that's in this problem is a multiplication. 5 times 10 to the second times 4 times 10 to the third. Well, when we do this, it does not matter which order we multiply our numbers together in, it's going to give us the same answer. So let's take those numbers that are similar. First of all, we have a constant of 5 and a constant of 4. What is 5 times 4? Well, 5 times 4 is 20. That takes care of the 5 and it takes care of the 4. That then leaves us with 10 squared times 10 to the third. What is 10 to the second times 10 to the third? Using our first law of exponents, that's 10 to the fifth. So our answer here, and let me raise that dot just a little bit up so that we don't confuse it with a decimal point. Our answer to this question is 20 times 10 to the fifth. Well, let's take it just one step further. What if I had said, I want the answer to be written in scientific notation? Well, in scientific notation, we have to have some number greater than 1 and less than 10 multiplied by 10 to some power. Well, here we have 20, which is not less than 10. So what do we do to this 20 to get it so that it's less than 10? Well, our decimal point, once again, is right after the ones place, after our 0. We have to move it left one time. So our new decimal place is going to be over here. Well, if we move the decimal place over here once to the left, what do we have to do to our power of 10, our exponent of 10? We have to increase it by 1. So 20 times 10 to the fifth is the same thing as 2.0. And since I got a decimal here, I'm just going to use an x here for multiplication, times 10 to the sixth. So our answer here without scientific notation was simply 20 times 10 to the fifth, but with scientific notation, our answer is now 2.0 times 10 to the sixth. Quickly reviewing, our first law of exponents states when you have some variable x raised to the a power and you're multiplying it by that same base, x, to the b power, your answer is going to be x to the a plus b. You add the two exponents together. And the stipulation is that a and b, in this case for the first law of exponents, are both positive integers. That'll wrap up session 51.